Okay, so let's go ahead and get started. So today, there's two main topics that we're going to talk about. One is what a universal gate is, and you'll see that there's two gates that are called universal. The AND gate and the NOR gate are both universal, and we'll discuss why. And then also today, we're going to go over two different forms of logic circuitry that we haven't talked about yet. So far we've talked about SOP, become a product, and then POS, product to come. But there's two other popular forms of digital logic circuitry. One is NAND, and the other is NOR. Okay. So just like previous classes, there's the lecture. The lecture will probably be just about an hour, and then you'll have time to work on the activity on these topics. And then you'll be able to finish lab 1. Okay, I mentioned last time that you could go up to both the POS and SOP output for that lab 1 problem that you have, but you wouldn't be able to do the third output, which is the NOR until after today's lecture. Okay. So first, what a universal gate is, it's a gate that you can use to make all the other gates. Okay, and here in class, I'm going to show you how you can use a NAND gate to make a NOT, to make an AND, to make an OR, and to make an OR. And then part of the activity is for you to do the same thing for a NOR gate. Okay, so these are the only two gates that are universal that you can make all the other gates out. So you can't make, or you can't use an AND gate to get all the other gates. You can't use an OR. Only the NAND and the NOR are universal. Okay, so we're going to start with showing how a NAND can be used as a NOT. And what's the relationship between the output and input of a NOT gate? Remember, a NOT gate is also called an inverter. Why is it called an inverter? What can you say about the output and the input of a NOT gate? They're always opposite, right? If you put in a 0 into a NOT gate, you're going to get a 1 out. If you put a 1 into a NOT gate, you're going to get a 0 out. Right? That's why it's called an inverter. So one way that you can use a NAND gate as a NOT gate is you take the NAND and you physically connect the two inputs together. So if I take a NAND gate and I physically connect the inputs together, what happens is you're forcing those two inputs to be the same value. Okay, now this is where having a circuits class can help. And again, you're not going to be tested on circuits, and circuits is not a prereq to this class. But if you ever take a circuits class, one of the first things you learn about is what voltage is. And when you connect things together, you make what's called a node. And a node has to have the same voltage. Okay? And remember, that's what these zeros and ones represent. A 0 usually represents 0 volts, and a 1 usually represents some positive amount of voltage. Okay? So when you connect these inputs together, you're forcing the inputs to be the same. So looking at a truth table of a NAND, when you connect these inputs together, you can only have the first row of the truth table or the last row of the truth table. See, once you connect those inputs together, it's impossible to have different output values. So these two rows of the NAND gate no longer apply. So look at the top row. If both inputs are 0, you get a 1 out. If both inputs is a 1, you get a 0 out. That's exactly what an inverter does. Okay? So you see, one way to get a NAND gate to act like a NOT gate, an inverter, is just connect the inputs together. Okay, so does anyone have a question about this? Is everybody good with this? Okay, because there's another way that you can connect a NAND to act like an inverter. And this other way is looking at just the bottom two rows of this truth table. So just, block out the first two rows. See, if I look at just the last two rows of this truth table, can you see that if I make one input to a NAND gate equal to a 1, the other input compared to the output is an inverter, right? Because see, if I make A equal to a 1, then the relationship between the other input B and the output is an inverter, right? Because if I make B 0, I get a 1 out. If I make B 1, I get a 0 out. So you see the output here would just be not B. So I have an inverter between the output and input B if I'm making A equal to 1. Okay? So yeah, there's two ways to make a NAND gate going on. So any questions on either of these two? Okay, makes sense? No questions? Okay, let's move on. Okay, now we're going to look how you can use NANDs, because you're going to see it's going to take more than one to do this. But we'll see how you can use NANDs to make an AND. Okay, so first thing is, and we talked about this last week, what is NAND short for? Not AND, right? Right, NAND is short for not AND. And what does that mean as far as, what is a NAND gate equivalent to that we talked about already? Like what other gate? Actually, two gates. The clue is not AND. You don't remember? What's that? I think you're thinking the Morgan, but not the Morgan. This was when we first talked about a NAND gate. We said, well, not NAND stands for not AND, and the NAND is equivalent to this gate with an inverter on the output. Yeah, an AND gate, right? That's why we call it not AND. Okay, that a NAND gate is equivalent to an AND with an inverter on the output. Again, that's why we call it a not AND. Okay, well, if I take a NAND, right, that's equivalent to an AND with an inverted output, and then I put another inverter on the output, right? So I have two inverters in a row on the output. What do you think is going to happen when you put two inverters in a row? Yeah, effectively they cancel out, right? So you see, this would be, right? This would be the same as an AND, right? Because the inverters cancel out. So now, to make this with all NAND gates, I'd have my NAND, right? Because like we said, AND with an inverter is the same thing as an AND. And now on the at the output of that NAND, I put a NAND that's connected as an inverter, right? So you see, I could just put another NAND with the inputs connected together because this acts like an inverter. Okay, so to make a NAND into an AND, you need two NAND gates. Okay, you just take a NAND gate and you put another NAND gate that's connected as an inverter at its output. Okay, does that make sense? Okay. No questions there? All right, the next one is when the Morgan's comes up. Okay. Okay, now let's look at how you would use NAND gates to make an OR. Okay, and remember, we talked about De Morgan's law last week, right? We talked about it first last week, but we've been using it, not only last week, but this week. We used it last class. Right? There's two parts to De Morgan's. What does De Morgan say about a NAND gate? It's equal to what? An OR with not just an OR, it's an OR with. Right, exactly, inverted inputs, right? And a NAND, by De Morgan's, a NAND is equal to an OR with inverters on the input. Right? That's what a NAND is equal to. Well, if I do this, right, again, if I put two inverters in a row, right, just like we put two inverters in a row here, and effectively they cancel out. Well, same thing here, effectively they cancel out, and you're just left with an OR. So this, like we said, by De Morgan's, is equal to a NAND. And now, if I put a NAND as an inverter at each one of these inputs, this here is equivalent to an OR. We say it takes 3 NAND gates to be an OR. This is usually the one that people have the most trouble with. But I think it's mainly just remembering this equality that we talked about with De Morgan, right? That a NAND is equivalent to an OR with inverted inputs, right? Now we're just adding these other inverters to effectively cancel them out, so we're just left with the OR. Okay, so any questions about this one? Everyone's good? All right, well, if you understood this, this should make sense, right? Because now to make a NOR gate with the NAND, and what does NOR stand for? Not OR, which is an OR gate with an inverted output. Well, look, we just came up with that. These 3 NANDs make an OR. So now all I have to do is take these NANDs that act like an OR and invert the output of this. Right? So the NOR is just going to be what we had for the OR. Right? So I'm just copying what we have up here. Right, so again, that's an OR. Now we just have to invert the output to make it a NOR. So we put another NAND gate as an inverter at the output. So those 4 NAND gates make an OR. Okay. So I would think a lot of you are probably thinking, so what? Well, why do this, right? Because, you know, last week we were talking about when we went over the SOP and TOS forms. Remember we talked about that it's good to know more than one form because one form is typically going to give you less gates. And the less gates you have, the better, right? Because the less components or the more reliability, less cost, all that type of stuff. So you may wonder, like, why do this? Like, if you can do an AND gate with just an AND gate, why would you use 2 NAND gates, right? Or if you can do an OR just with a single OR, why use 3 NAND gates to do it? Well, the reason for this used to be more important, you know, back in the day. You know, back when I was your age, or not even that long ago, maybe up to about 20 years ago, but still your entire life, I know. You know, this used to be more important than it is now, because now we have these programmable ICs like the FPGA IC that's on your basis board, right? That has all different logic circuitry inside that you can pick out with software. But you see, back in the day, these gates used to come in individual ICs. Like you would have an individual IC that had all inverters inside. It only had inverters. And you would have another separate IC that had just AND gates inside. You know, and another separate IC that just had NOR gates, and another separate IC that just had AND gates. So you see, back then, if you could do your design in all the same gates, then your purchasing department, wherever you worked, was very happy because they could just bulk order that one type of IC instead of having a bunch of different ICs. And of course, when you bulk order something, you get a good price on it. So, you know, sometimes it was more cost effective to do everything in the same gate. But like I said, that's not so important anymore because we have these programmable ICs. So that's, you know, at the component level. But still, this can be important for engineers that design circuitry in silicon. Okay, like the actual circuitry that's inside the IC. Now, I know the EE students, when they think their circuits one class, manufacturing is taught in that class. So you learn a little bit about how ICs are made. CPE students, I'm not so sure now because there's that new circuits electronic sequence, the, what is it, the one, is it 115, 215, 315? That I would imagine most of you are on because I think it started this last fall. So I'm not so sure. I wasn't involved with developing that class or those classes. So I'm not so sure how much manufacturing is covered in that class. But if you ever take a class in manufacturing of ICs, or if you just go, you know, on Google or, you know, search the internet, you can find information on it. You'll see when they make ICs, they use imaging techniques. And they use what are called masks, which have the image of the circuitry, and they shine UV light onto some silicon. And when you're using all the same gate, it's more cost effective because your mask that you're doing the imaging with is all the same. Like you don't have different ones, right? So it just becomes more cost effective. So even though this isn't as important as it used to be, it's still something that's good to know. It just depends on what particular area that you go into. You know, if you work at some microprocessor manufacturing place, you know, this could be handy. But if you're doing all component level stuff and you use a programmable IC, well, then it's not so important. Okay, but like I said, here in class, you know, I showed you how to do these gates with NAND. One part of the activity that you'll do is do the same thing, but use noise. And it's the same approach. It's the same thought process. Okay. All right. So any questions before we move on? Because we're going to move on now to NAND and NOR if you don't have questions on this. Everybody's good? Okay. So the next thing I'm going to show you is how to go from SOP, right, sum of products, to NAND. Okay, so here's our SOP equation, and this might look familiar, right? Because this comes from the example from last week with the, you know, E stands for eat, and C for chips, and G for eggs, and S for salsa. Remember that example? And so it's the same equation we had last week for that example. So this is SOP, right? And this was also from that same example, and you may remember this is the POS. Okay, but starting here, the first thing we're going to do to turn this SOP equation into a NAND is we're going to double knot each side of the equal sign. All right, so we're going to double knot here and double knot. And of course, when you double knot, you don't change it. Now, also, like we talked about, if you have a double knot over the same variable, well, that's the same as just the variable. Okay, the next thing we're going to do is we're just going to look at this part of the equation. Like, we're not going to worry about this top bar yet. We're just going to look at this bar here and what's underneath it. So, looking at just this, you have this term that's ORed with this term, that's ORed with this term, which is ORed with this term, and then the whole thing knotted. So if you're ORing multiple things and then you're knotting the whole thing, what kind of gate is that? What is it? Yeah. If we're ORing, then inverting the whole thing? NOR. NOR. Yeah, that would be a NOR. I erased the other. Let me fix that. Let's see. I got rid of my black here. This is a knot here. I just don't want to lose that. Right. This is a NOR. Okay. And then from De Morgan's, we know a NOR is the same as what? And with inverted inputs, right? And you see our inputs here are these terms. So you see, this is a NOR with inputs, not C, G, not S, not C, G, S, C, not G, not S, C, not G, S. Again, keep an eye out. If I make an error, like I forget a not or something, please let me know. But like what was just stated, this NOR by De Morgan's is equivalent to an AND with inverters on the inputs. Okay, so we're going to take each one of these inputs, right? Each one of these terms that's an input. We're going to NOT it and then add it and it to the next term. So you see, I'm taking this input here, not C, G, not S. I invert it. Then I'm going to AND it with the next term inverted. Right, the next input inverted. Right, AND it. AND it. Okay, so you see this NOR gate is equivalent to the inputs of an AND inverted. Now, remember, we ignored that top bar, so that's still there. All right, so you see, I take my SOP, I NOT each side of the equal sign twice, I do De Morgan's once, and this is NAND. Right? You see why it's NAND? Because each term, right, we're ANDing and then NOTing the whole thing, right? ANDing, excuse me, we're ANDing, then NOTing the whole thing, ANDing, then NOTing the whole thing, ANDing, then NOTing the whole thing, ANDing, then NOTing the whole thing. So each one of these terms is a NAND gate, and then we're ANDing those terms together and NOTing the whole thing. So that's also a NAND gate. Okay. Remember last week with SOP, we drew the logic diagram, right, that showed the gates. And do you remember for an SOP what kind of gates we have? For SOP, you're ANDing. Yeah, again, for SOP, we wouldn't have those top bars, right? So for SOP, you're ANDing, right? ANDing, then you're ORing, right? So what kind of gates would you have? Say that again? Right, multiple ANDs and an OR. I mean, here we have 4 ANDs, right? Because we got 4 terms. And then we have 1 OR gate. Well, with NAND, you're NANDing multiple times, and then you're NANDing one big time after that. So you see, all your gates are NAND gates for a NAND. That's why it's called NAND. Right? So you see the logic diagram for a NAND is you're going to have multiple NANDs. And these would all have 3 inputs. Right, this NAND gate, if I make this input not C and this G and this not S, right, this NAND gate's going to give us this term at the output. Right, and then the next term. Right, the next term. Sorry, sometimes my G's look like 6s. That's a G. This one here. Right, see, you need a NAND gate for each of these terms. And now another NAND gate, right, where these outputs go into the inputs of this NAND gate. And then at the output of this NAND gate, that's where you have your NAND expression, right? It's going to take each one of these, AND them together, and then invert the whole thing. Okay, so does that make sense? You know, I suppose you know, SOP, which has multiple AND gates than an OR, I suppose, you know, you could call that an and or, you know, but for whatever reason, they don't. They call it SOP for summer products because, like we said, if you look at this as a base 10 equation, it looks like you're multiplying and adding, right? But you're actually ending an or. Okay, so any questions about what we did here? You have a question?
Okay, so those bottom pieces would have an not over.
Oh, maybe, because I don't know, where are you pointing to?
Like the output of the first menu.
This one, right? Oh, right here. Yes, you're right. Thank you. Yeah, like I said, thank you. Yeah, I just forgot to put the knots across. Good. Okay, any other questions? All right. If this made sense to you, the next thing we're gonna do, go from POS to NOR is very similar. Okay, very similar. So we start out double knotting both sides of the equal sign. Okay, so again, that's the same as just E. Now we're looking just at this bar and what's underneath. Okay, we're ignoring the top bar. So look, just looking at this part of our expression, we have this term, ANDed with this term, ANDed with this term, ANDed with this term, the whole thing knotted. So what kind of gate is that? You're ANDing and then knotting the whole thing. Okay. That's a NAND, right? So this is a NAND. See, this is a NAND with inputs C or G or S, C or G or not S, not C or not G or S, not C or not G or not S. And then from De Morgan's, we know a NAND is equal to what? Say that again?
An OR with inverse inputs.
Yep, exactly. An OR with inverted inputs. Correct. So an OR with inverted inputs. So I take each one of these inputs, I invert it, and then I OR it. Okay, so take this input, right, invert it, and then we're going to OR it. With this input, that's inverted, OR it with this input, that's inverted, and OR it with this input that's inverted, right? So that's going from this NAND to this equivalency, which is an OR with inverted inputs, and then we got to put this bar back. So look what we have. This is a NOR gate, right? Because we're ORing these and then inverting the whole thing, right? This is a NOR, this is a NOR, this is a NOR. And then these NORs are being ORed together and the whole thing inverted, so that's also a NOR. So what do you think the logic diagram of a NOR is going to look like? Here's the NAND. What do you think the NOR is going to look like? It's just going to be all NORs, right? We have 4 NORs. You know, they have 3 inputs, right? 3 inputs. And then the outputs of these NORs would go to one big NOR here. Right, and at the output is where you would have this equation. At the output of each of these NORs, you'd have this separate term here, right? Like this term would be here, let's say, you know, if we made this C, G, S, here we would have C or G or S, the whole thing inverted, right? And it would be the same thing, you know, like this term would be for this one, this term for this one, this term for this one. Okay, so people Does anyone want me to actually write that, or you get the idea, right? It's very similar to what we did over there. It's just NORs instead of NANDs, right? Okay. All right, so how are we doing? We're doing good on time here. We'll probably finish the lecture by the top of the hour, so that's good. But any questions? Everybody's good up to this point? Because now it gets a little bit more complicated. Okay. I mean, when you're first learning something, you know, it's never totally easy, right? Because it's new. But relatively speaking, when you go NAND to SOP or SOP to NAND, or NOR to POS or POS to NOR, that's fairly easy. Right? Because if you look at what we just did here, you know, going from SOP to NAND, it was just doing De Morgan's once. Well, you had to double knot each side first, but then you're just doing De Morgan's once. If you think back to last week when we went from SOP to POS, that was De Morgan's twice. So, you know, this compared to what we did last week is easier, right? Because it's one less step. Okay. Also, to go from NAND to SOP, do you see that all you have to do is see each of these terms right here are the terms in the SOP. So when you go from NAND to SOP, you just keep these same terms and change these ands to ors, right? You effectively just get rid of all these knots and just keep the terms and change these ands to ors, and you're back to SOP. Okay. Over here, right, if you go back to what we started with, the POS, and compare it to the NOR, it's the same sort of thing. To go from NOR to POS, you keep the terms that's in your NOR and just change the ors to ands, right? You effectively just get rid of the knots. All right. So no matter which way you're going, okay, when you're doing these conversions here, it's not that bad. You know, granted, everything at first is not real easy, but again, we're talking relative here, okay, to other things. Well, going from NAND to POS or NOR to SOP, that requires more work. And that's what we're going to do next. Okay. And you're going to see when we do these examples, we have to go through a K-map. Okay, remember we talked about kernel maps last time? Okay, well, here's another situation where kernel maps are important. Or just got to erase that's a C. Okay, so I'm going to show you how to go from NAND to POS with an example. So here's the example here. So what kind of expression is this? I'm ANDing, then inverting the whole thing, right, to get each one of these terms, and then the terms are ANDed, and the whole thing's knotted. So what is that? Yeah, this is NAND. It's just like what we have over at the left here, just different variables. So the first thing we want to do here is we want to take this NAND and write it at SOP. So like I just mentioned a moment ago, when you go from NAND to SOP, you're just taking the terms and ORing them together. So we're going to take AC, OR it with not CD, OR it with not A, B, not C. So again, you effectively are getting rid of the knots up top and just changing these ands to ors, and that gives you the SOP. Okay. Now we're going to put this SOP equation into a kernel map. Now, last class, you know, I did a bunch of examples and you had an activity where the kernel map was filled out, right? The kernel map had the zeros and ones. And then from the kernel map, you would write the equations. See, here we're going the other direction. Here, you're given the equation and you got to fill out the kernel map. So it's sort of like you're doing reverse of what we did last time. Okay. And, you know, if you can do something both directions, that's usually a sign you have good understanding. So now, since this is an SOP for F, what am I going to write in the Carnot map? Am I going to write zeros or ones? Since it's an SOP for F. Ones, right? Yeah, remember. SOP for F goes with ones, SOP for not F goes with zeros, right? Okay. So what am I going to write in my Carnot map for this term AC? Do you remember when we talked about Carnot maps, what number grouping is a two variable term? 4. Right, so we're going to have a group of 4. So where is that group of 4 going to be for term AC? Where's it going to be? Right, down here, right? Everybody agree? Right, because see this group of 4, it's in row A and it's in column C. Okay, so we took care of that term. How about not CD? Right here?
Everything that's on the bottom where it's not.
So which 4 cells, can you give me the numbers?
So the first one,
Okay, this is cell 1, so cell 1,
the ones that have that.
this one? This is, do you want to come up and put the ones? Might be easier just to do that way. Okay, so we want not CD. Okay, now remember, it's a two variable term, so it should be a 4 grouping.
That would be.
Right? Yeah. There you go. All right. Yep, that's it. Thank you. Yeah, so it's this 4 grouping here, right? Because this 4 grouping has not C and also D common. Okay. All right, so now we have this term, not A, B, not C. So it's a 3 variable term. So what number grouping is that? 2. Okay, so what 2 cells? 4 and 5, right? Right, 4 and 5 because it's in the not A row, B row, and also not C column. Okay? So we get where the ones are in our Carnot map from our SOP for F, and now all the other cells are 0. These are all going to be 0. Okay, now before we go any further, let's think about again what we're doing here. We started with nan, and we want to get POS. So since I want POS, what do I got to start with? Say it. SOP for nada, right? Remember? Right, we've done this a number of times, right? That if you want POS for F, you got to start with SOP for not F, right? Because once you have SOP for not F and you do De Morgan's twice, everything inverts, right? Ands to ors to ands, right? Okay. So I want to get the SOP for not F now. So since it's not F, what am I interested in this K map? Zeros or ones? Yeah, the zeros. So I got to group the zeros to get the SOP for not F. Okay, so how are you going to group the zeros? Where are you going to start? Yeah, exactly. This 4 grouping right here. And what term is that 4 grouping going to give us? Yeah, not AC. Yeah. Very good. Thank you. Okay. What would you do next? You got these other 3 zeros that you haven't accounted for.
You can do 12 and 8.
12 and 8. Okay, that sounds good. 12 and 8. And what term is that gonna give us? What's that, A? And what? Not C, yeah. Not D. Everybody agree with that? These this two grouping is common to A, not D, and also not C. Yeah. Okay, and then we got another 0 here. What are you gonna do with that one? 8 and 0, okay, that's what I did. Does anyone see another grouping they could do instead of 8 and 0? Yeah, you could do 2 and 0 also. So here's an example of there being 2 correct solutions. Okay, I did 0 and 8. My 2 previous sections chose 0 and 2. So you're the first section today to do it the same way I did, but either way is correct. So what term is 0 and 8 going to give us? Not B and what? Not C and not D, right? Right, everybody agree with that? Okay, so we got the SOP for not F, so now POS for F, right? Everything gets inverted, ands to ors the and. So again, keep an eye out, make sure I don't make a mistake. If I make a mistake, let me know. So it's A or not C and with not A or with C or with B and with B or C. So let's make sure, right? I inverted everything, right? And these ands went to ors. These ors went to C. I highly recommend that just like what I'm doing, double checking, you do the same thing, because it's very easy to miss inverting something or miss, changing an and to an or to and. So I always double check because it's just very easy to make a mistake when you do that SOP to POS, or if you go the other way too. Okay. Now, this problem didn't ask for it, but look, once you have POS, you can then in one step go to NOR, right? Because if you just do De Morgan's once, right, you can go from POS to NOR. So if we went one more step, we would be going from NAND to NOR. Okay, but the main thing to take from this is you got to go through a K-map when you're doing NAND to POS. Okay, so any questions before we do the next example? Because if you understood this example, this next one's similar. Okay, so this is NOR to SOP. So we're using this example here of this NOR expression. So like we said earlier, to go from NOR to POS, you're just keeping the terms and changing these ors to and. So the POS would just be A or C and with not B or C, right? So you see, I'm just keeping the terms and changing that or to an and, right? And I'm just, effectively you're getting rid of the knots up top, right? And you're just changing that to an and and keeping the terms. Okay, so everybody see what I did there? All right, but now I want to go into a K-map. So going into a K-map, just like going into a truth table, what form do we want? SOP, right? So the next step is to take this POS for F and go to SOP, which is going to make this what? Is this going to stay F? If I go POS to SOP, what happens? Everything gets inverted, ands to ors, and ors to and. So this is going to be not F. And then we're going to have not A, not C, or with B, not D. Right? So since this is SOP For not F, what am I gonna put into this K-map? Ones or zeros? Zeros, right? Not F is where the zeros are. So let's take this term first, the not A, not C term. Where are you gonna write the zeros for that term? It's two variables, so how many, what's the grouping? 4?
It would be 0, 1, 4.
Yeah, exactly, right here. Right, because that 4 grouping is in the not A rows and the not C columns. Right? So that takes care of that. Okay, how about B, not D? Yeah, 6, 14, because remember, these edges touch. So we got a 4 grouping, 6, 14, 4, and 12. Right? So that would be the B, not D. Okay, and then everywhere else are ones. Okay, so now we're gonna circle the ones and we're gonna get SOP for F. Right, which is what we want, right? We're going from nor to SOP. Okay, so now we gotta group the ones. So how are you gonna group the ones? Any ideas?
So
Say that again?
CNG, so 37, 15, and 11.
Okay, so this column here. These 4 in this column. Right, and what'd you say the term was gonna be?
CNG.
Yeah, CD, right, because it's in the C and D columns, right? So it's gonna be CD. Okay, what would you do next? 13, 15, 9, 11. 13, 15, 9, 11? Okay. Okay, so these 4 here, what term is that gonna give us?
D.
B? Is it gonna, we're looking at this one right here. These,
Oh, A and B.
yeah, 80. Oh, there you go. All right, we still have some ones not accounted for, right? We got these down here, that one. So what would you do next? Whole bottom row, okay. A lot of overlapping going on here, huh? But remember, overlapping is good. Or can be good. All right, so what term is this gonna give us? Yep, that's A, not B. All right, and we got one left here. We haven't counted this. And remember, just like the sides touch, the top and bottom touch.
Before, 11, 10.
Okay, 11, 10. Okay, yep. Yeah, so it'd be like that. Right, so it'd be this 4 grouping here. So what term is that grouping gonna give us? Not what? Not BC, yeah. Okay, so you see, we got SOP, and you could go one step more, right? Because once you have SOP, it's easy to get the NaN. Okay, we weren't asked to do that, but you know, you could do that pretty easily. Okay, but again, the key thing, you had to go through a K-map. All right. Okay, so there's just a couple more things I want to mention before you can start working on the activity today, and then after that, you know, work on lab 1. The activity, let me show you on Canvas. Now, also, before I pull the screen down, here are my answers to the activity. And then also, here is the black box diagram, or an example of the black box diagram for lab 1. I've been getting a lot of questions about black box diagrams. I can understand why, because when I talked about them, I didn't spend a whole lot of time on them. And the reason I didn't spend a whole lot of time is they don't really, in my opinion, you know, require a lot of time, because all a black box diagram is showing you is what the main inputs are and the main outputs. So for your lab one, you have 4 input, and you're gonna have 3 outputs. Okay, like I mentioned last class, after Tuesday's class, you only knew enough to do 2 of the 3 outputs, right? Because at that time, you didn't know about NAND, NAND, and NOR, so all you could do was SOP and POS. But now that you know about NAND, NAND, and NOR, we want you to include a 3rd output, a NOR output. So in your design source file, where now, I would think most of you have equations, assign a statement for SOP and POS. Now you can add a 3rd line, okay, a 3rd assign for NOR. Okay, so if you were able to get a successful simulation for your SOP and POS, all you have to do to finish lab 1 is add a 3rd equation for NOR. You'll have to add a 3rd output for NOR, both in your design and your sim file. You'll run your simulation again to make sure all 3 outputs are correct. Now, should all 3 outputs give you the same thing? Should they all be synced? Should your SOP, POS, and NOR have the same? Is it giving you the same truth table? Yeah. Yeah, these are all logically equivalent. That's the main point here. So when you're testing your lab 1 design on your basis board and you're going through the different combinations, and since there's 4 inputs, how many different combinations are you going to have? 16. So in your video, to show that your design, your lab 1 design works 100%, you got to show all 16 inputs of your truth table. And those 3 lights that show the SOP, POS, and NOR outputs, they should all be in sync. So they should be all off at the same time. They should be all on at the same time. If they're not, like if you have 2 that are in sync and 1 isn't, chances are the one that isn't, your equation's not correct. Either why it wouldn't be the same. Okay. But yeah, the whole main point of this lab is to show that these different forms of equations, they're logically equivalent. They give you the same truth table. This on. Here. Okay, so there's 2 documents for the activity. This and they're on Canvas under Meeting4. So this is the one where I want you to use NOR gates for an OR, a NOT, and an AND. Also include NANDs. There should be NANDs here. So just like I did 4 different gates with the NAND gate, I want you to do the same, 4 with the OR gates. Okay. And then the other part of the activity, or the other document, right here. Okay, the first part is I want you to draw the reduced NAND circuit. When I say circuit, I mean, this here. Now, in this class, anytime you see the word reduced, what should pop up into your head? K-map, exactly, because that's how we reduce equations, right? So you're going to have to use a K-map, put this truth table into a K-map, get the reduced expression from the K-map, and then get it to be a NAND, right? So you're basically doing what we did over there. Okay, and then draw the diagram. And then the second part of this is you're given a NAND expression, get the NOR from it. And that's similar to one of the problems we just went over. Okay? And then the lab, like I said, the lab part 2 is just adding a 3rd output. Right? So if you've got the sim for the POS and SOP already done, all you got to do is add that 3rd output, sim it again. If your sim is good with 3 outputs, then you're ready to download to the board. Okay, there's no reason to download to the board until you have all 3 outputs. Some people in my previous section, they were downloading with just the 2 outputs, which is fine, but you're gonna have to download again because you got to have the 3 outputs before you turn it in. Okay? All right, so do you have any questions before you get started today? Just like previous classes, work on the activity first. When your group is done, make sure you pass it in so you get credit. And then after your group is done with the activity, then work on the lab. And again, you have to be physically present for the activity to get credit. I had a student in my early section today leave the room after, about 5 minutes after the activity started. So that person's not going to get credit. Okay, you got to be physically present, working with your group, hand it in. If you leave earlier than that, you're not going to get credit. Okay? All right, so any questions before you get started? All right, well, I'm here if questions come up, and Blake will be here in about an hour.